Hi everyone, in this video we are going to learn permutations. This is the second video of probability, uh, this topic. Permutation is another way to count how many different outcomes for a given event. Now these are our objectives. First, we want to know what is called a permutation. Secondly, we are going to use fundamental counting principle to calculate a permutation, the permutation. And then we are going to develop a formula for permutation, during which we are going to encounter this terminology called factorial, which is a calculation and which is also very easy to do. And last one, we are going to use a calculator to calculate a permutation. So eventually we are going to use calculator. It's very easy to do, but you have to understand the concept before you can get the right answer. Even though the calculation part is easy to do, there's something that is important than calculation, which is being able to identify if you have a permutation problem or not. If you have a different problem and you use a permutation formula to do that, you're going to get the wrong answer really fast. Okay, now let's start with the definition of permutation. Basically, permutation is arrangement of items or people. And there's two characteristics, or there's two things you need to consider if you have a permutation. First, in this arrangement, no item is used more than once. For example, if you want to arrange these three letters A, B, C, you cannot use A, B because you use A twice. Okay, each item can only be used once in one arrangement. Secondly, and more importantly, this is a characteristic of being a permutation. So it's super important. It says the order of arrangement makes difference. In other words, whenever the order makes difference in your arrangement, it is called a permutation. So for example, if ABC is different than ACB, it will be considered a permutation, such as when we create a password, order matters, right? Order matters a lot. Even if you have same three letters, ABC is not CBA as a password. So whenever order matters, it will be a permutation. We make that judgment in terms of real meaning actually makes difference the order in real life. It's not that say that we just try to remember these rules. Okay, let's look at our first example. You need to arrange 7 of your favorite books along a small bookshelf. How many different ways can you arrange the books? Assuming that the order of books makes difference to you. So we are told that the arrangement of these books makes difference. So it is a permutation. Let's make that clear, right? Now we are going to calculate, we are going to count how many different ways to arrange these 7 books. Now, even though it is a permutation problem, we cannot use a permutation formula because we have not learned it yet. So we are going to use this fundamental counting principle to do the calculation to get the right answer. Then later on, we are going to develop this permutation formula actually. After that, we can use the formula whenever we have permutation scenario. Okay. The reason we can use the fundamental counting principle is because this process can be broken down into steps. You have 7 books. You can put these 7 books one by one onto the bookshelf. So that's like steps. So now let's just do that like in real life. This is a bookshelf. And we're going to put 7 books in here. And you have the 7 books sitting on the table, okay? Sitting on the table. And we're going to put 7 books onto the bookshelf. Now we do it one by one. And the fundamental, try to recall the basic meaning of fundamental counting principle. In that principle says, you can break down the whole task into several steps or several components. Then you focus on how many different ways to do each component. Then multiply them together. The result will be how many different ways you do the whole thing. So they ask us how many different ways to put the 7 books on the bookshelf if order matters. So we focus on how many different ways to do each book, then we multiply them together. So since there's no restriction on which book could be the first one to be put on the bookshelf, any book is randomly, has equal chance to be selected to be put on the bookshelf. So for the first book, there will be 7 different ways to do the first book. Let me draw this box to indicate which the books. 1, 2, 3, 4, 5, 6, 7. It's like invisible. You don't have to draw this. Just indicate this is the first book. Since there's no restriction which one should be the first one to be put on the bookshelf, we have 7 different ways to put the first book on the bookshelf because there are 7 books available. Now, after you put the first book on the shelf, there's only 6 books left. So now we need to figure out how many different ways to put the second book on the shelf. Apparently, there's 6 because any of the 6 can be put on the bookshelf as the second one. And the rest are very similar. Then 5, 4, 3, 2. I only have 1 book to pick. There's only 1 book left. There's only 1 way to do that. Pick that book. So according to the fundamental counting principle, you need to multiply them all together. That's how many different ways you put all the 7 books onto bookshelf. So let's do the calculation using the calculator. 7 times 6 times 5 times 4 times 3 times 2 times 1 equals 5,040. That's why we learn fundamental counting principle. There's no way to figure out how many without that. So more than 5,000 different ways. They're all different way to line up these 7 books on the bookshelf. Okay, now let's look at our terminology. It's also, you can call it concept called factorial. So look at this calculation we just did, 7 times 6 times 5, 4, 3, 2, 1. And this kind of multiplication is called a factorial. Since it started with 7, we call it 7 factorial. If it started with 10, we call it 10 factorial, and so on. And written as this, 7 with exclamation mark, which is the operator in mathematics. Just like plus, minus, multiply, and divide. It's just different operator to indicate you start with 7, you multiply all of this number together down to 1. That's called a factorial operation. We don't need to go through this definition as long as you understand what a factorial is. Now let's use a calculator to calculate this 10 factorial. That means start with 10 times 9 times 8 down to 1, right? All of those numbers in between. Now you wonder how big or how much bigger this 10 factorial compared to 7 factorial, right? We know 7 factorial is 5,040. We just did that, even though we didn't do the factorial part. Maybe let's do it now. Factorial operation is part of a probability. And if you have a scientific calculator, it's almost guaranteed you will have that factorial operation built in. And for some calculators, you see a button dedicated to that operation. For some other calculators, you don't have that. Instead, you have another button, which is called probability. PRB, I believe. I don't have that calculator. It's like $12, maybe it's $13 calculator. Mine is like $12 calculator, by the way. Just don't have same type. So if you don't have this button, which usually display as exclamation mark or just exclamation mark, that's for the factorial operation. If you don't have this, look for PRB, which represents probability, or PBR, I forgot, maybe PRB. Put this button under this button, it will display on the screen. This is three. NPR, NCR. The next one, last one is this operation. Okay, now let's use my calculator to demonstrate this. First, you always input the number because calculator needs to know which number to start to do that multiplication. So in our case, it's 7. Then exclamation mark for my calculator, you can see it right here. So it's between two buttons. That's why we need to push this shift button. Then push this button below, and then exclamation mark will show up. See? Then we are ready to push the enter button. 5040. Now we do 10 factorial. Apparently 10 is only 3 bigger than 7. It's less than 50% bigger. Now let's see how much bigger 10 factorial is. So 10 factorial button equals, well, let's write it down. Let's write it down. So this equals 3628800. More than 3.5 million. This is many, many times bigger than that, even though the number itself is less than double for sure. So factorial calculation is a very powerful one. It's getting bigger really, really fast. Okay, now since we have this factorial done, now let's develop the permutation formula through this example. You and 19 of your friends have decided to form a business. The group needs to choose 3 officers, a CEO, an operating manager, and a treasurer. In how many ways can these offices be filled? Basically, we choose 3 people out of 20, you and 19 of your friends, 20 people, right? So basically, we choose 3 out of 20. Order makes difference. Now let's make that part clear before we do calculation, because later on, if you cannot identify this is the permutation problem, you're going to use the wrong formula. When we say order makes difference, or order makes no difference for that matter, it refers to the selected item, the order you arrange the selected items or people. In this case, the order of the 3 selected officers is not the order of all of those 20 people. It's the selected items. Now let's look at this to see if this makes sense to you. We have 3 positions: CEO, manager, and treasurer, right? Now think about this. If this makes difference to you or not among select 3 people, let's use ABC to represent the names of those 3 people selected to assume these 3 different roles, different positions. Let's say A being CEO, B being manager, and C being treasurer. Is it the same outcome as, say, B is the CEO, and A is the manager, and C is the treasurer? Do you think this is the same thing? I don't think this is the same thing, because apparently, even though we have 3 different same 3 people, but they assume different roles. The first outcome is that A is CEO. The second outcome is that B is CEO. The CEO has these 2 outcomes is different outcomes. Just like when we select as government officials, let's say president and vice president, you say we have 2 people. Let's use the current government as example, maybe easier to understand. Say we have a president and vice president, these two positions for the federal government. And currently, Biden is the president and Harris is the vice president. Imagine what if Harris is president? Again, same two people, right? And Biden becomes the vice president. Do you even call these two different scenarios the same government? Same two people, right? Order make huge difference. In this order, Biden is the president. We are going to call it Biden administration. In this order, Harris is president. We are going to call Harris administration. It's totally different government, even though the same two people. So order matters. Whenever order matters among the selected one, it is a permutation problem. So make sure you understand it refer to the selected items, not the candidates for that selection. Okay, now since we have now developed that formula, again, we are going to use fundamental counting principle to solve this problem first. How can we do that? Just literally imagine in real life, we need to vote to get the three people to assume the different roles. So let's do it that way. So we have three positions here. CEO and the manager and treasurer. Now 20 candidates here. We need to select these three people out of the 20 people. We do it one by one. So we can use the fundamental counting principle, break it down into three steps. And since there's no restriction on who can become CEO, who can become manager, who can become treasurer, anybody can be in any position. So no restriction. So let's select the CEO first. How many different ways to select CEO? Apparently 20, because no restriction. Anybody can be CEO in this 20 people group. And after we select CEO, there's only 19 candidates left. Don't forget that, like real, treat it like real. Now we need a manager. We vote again to select manager. And there's 19 different ways to do that because there's 19 possibilities. Anyone could be manager. So there's 19 of them. Similarly, for treasurer, there are 18 of possible ways. Multiply them together. That's our final answer. How many different ways to fill these three positions? 20 times 19 times 18. 6,840. That's how many different ways to fill these three positions. Now let's use the same example on the next page to develop the permutation formula. Now our goal is to multiply these three numbers together. We already did that. We already got an answer. Now let's look at this calculation a little bit different way to do this calculation. Instead of multiply the three together, we get an answer. I can continue to do this multiplication. 17, 16, 15 until I have 1. You may wonder why we do that. We already got an answer, right? Exactly. We want to derive that formula. That's the goal. So getting answer is not the goal for this part. And this apparently is called a 20 factorial, right? 20 factorial. We already learned that terminology. Now, the thing is, we don't want this 20 factorial. We only want the result of these three multiplied together. In order to achieve the goal of these three numbers multiplied together, I have to get rid of this, right? How to get rid of that? This whole thing divided by 17 times 16 times 15 until 1. The thing about that, like simplifying fractions, they can be canceled again. So you don't actually cancel that. If you actually cancel that, what's the point? We already have did this 20 times 19 times 18. Now this part on the bottom can be written as 17 factorial, right? So this three number multiplied together actually equals 20 factorial divided by 17 factorial. Now we can also rewrite 17 as 20 minus 3. That's 17 for sure, factorial. Why do we do that? Why not 17? The reason is very simple. 17 didn't appear in the original problem. Only 3 and 20 appeared in the original problem. We select 3 officers out of 20 candidates. So when you have original problem description, you have to use original number appeared in the original problem. You cannot use different numbers. That's why we have this. This will give us how many different ways to select 3 officers. Now, how we represent that symbolically? First, we select 3 out of 20. So we need these 2 numbers. Secondly, it is a permutation. We use a P, first letter of that word, as a symbol. This is a permutation problem. So overall, this means we have a problem that is permutation problem. We need to select 3 items out of 20 items. And this is how you do that in terms of calculation. Now we generalize. This is the number we need to select. This is the number we select from. And this is a permutation. When we generalize that, we get something like this here. So n represents the total number of items. N represents items, number of items we want to select. And this calculation equals n factorial, total number factorial. This is like 20 here, total number factorial. And n minus r, just using this total number of item minus the number of item you want to select. Same thing here, and factorial. This is just a general formula to calculate how many different ways to select r items out of n items. So this is just a formula. We are going to use the calculator to do the calculation, but understanding the scenario in which you can apply this formula is very important. In other words, how do you know you have a permutation problem? First, the order in which those you select those R items matters. They're important. They make difference, and that's a characteristic being a permutation. And then after that, the calculation part is easy to do. All you need is identify, you select certain number of items out of another certain number of items. That means you don't need the fundamental counting principle because you don't break it into different components. You don't follow steps. You just select a certain number of items out of another certain number of items. That just tell you have permutation problem. Now I'm going to redo this one. We already got the result of this, okay, which is apparently equal to 20 times 19 times 18 because this 2 will be canceled, which is equivalent to this. Now we do this using the calculator. Maybe I use this formula once, at least you can see it. Select 3 out of 20 equals 20 factorial, and this is 20 minus 3 factorial. According to the formula, 20 factorial is 20 times 19 times 18 times 17 until I have 1, right? This is 17 factorial. 17 times 16 times 15 until I have 1. Apparently, they're all the same, this part. You just have the same thing as our original. We're going to 6,840, I remember from the last calculation. Now let's use the calculator to do the same thing. Select 3 out of 20 permutation. Now first, you always input n, the number, the total number of items first, then find this NPR button. This is the procedure to do that. Input 20, then put this NPR button, which represent permutation, then input 3, then equal button or enter button. So I'm going to do just that. 20. And for me, this is the button I'm going to use. You see here, NPR, here, NPR. Above X, this button, NPR. So you see in between, I need shift button. So I push shift. And then I push this X, I get P. So it display as P, you don't push letter P if you have upper level calculators, you can type text actually, those alphabet letters. In that case, don't type P. P is not permutation. This is just a symbol of permutation. It's from NPR. Okay, you don't push P. Now I need to input 3, then equal 6,840. The exact same answer. Okay, now let's look at our second example here using this formula. 6 performers are to present their comedy acts on the weekend evening at a comedy club. How many different ways are there to schedule their appearances? Now, try to figure out the scenarios. Okay, understand the information. You have 6 performers, and they're going to go on to the stage to perform their acts. First thing is to realize this is a counting question. They ask us how many. We have to count how many. Whenever you do counting problems, there are 3 different ways to do that. Fundamental counting principle, permutation, and later on, combination. So how do we know which one is which? And this one first can be done using fundamental counting principle because it can be broken down into steps. 6 performers are going to present their acts on stage one by one. So there's the steps. First one, second one, third one, and so on. So we can do it using fundamental counting principle. We can also do it using permutation. The reason, first of all, 6 performers, they are candidates to perform, right? To go on to the stage. They are going to be, all of the 6 going to be selected. So we select 6 people out of 6 people in this case. And the order matters. Everybody understand who is going to perform first, who is going to second. In the theater, makes a lot of difference. Just like people give speeches in the big conference. Who is the first, who is second, it's not random. There's a reason for the order. For example, if you invite a keynote speaker and among other speakers to give a speech in the conference, you don't really want that keynote speaker wait until to be the last one to give a speech where everybody get tired and ready to go home. That's going to be a disaster. Next time, no keynote speaker will come will accept your invitation anymore. So order makes difference. So this is a permutation problem. So we can use P 6 out of 6 because order matters, and we select certain number of items out of another certain number of items. So either way is okay. Later on, we mentioned the difference between permutation and combination. For now, this is a combination problem. So we can use the fundamental counting principle first. When you do your homework, you don't need to do both ways. It's just to show you how to approach a problem when you have a new problem. So imagine I need to select 6 people to go onto the stage. In the beginning, all of the 6 people are available, and there's no rule regarding who should be first, who should be second. So anybody could be any place to be put on the stage. So for the first person, there are 6 different ways to select first person because there are 6 candidates. Anybody can be the first. After you select the first one, now this is the order. Okay, 1, 2, 3, 4, 5, 6 to go onto the stage. Now for the first one to go on the stage, there's 6 different ways because 6 candidates available. After the first one is already determined, when you determine who is going to be second, right? By that time, there's only 5 candidates left. So there are 5 different ways to do this one. And the rest are very similar, 4, 3, 2, 1. When you multiply them together, you see, this is like 6 factorial. When we do that, 720. So there are 720 different ways to arrange these 6 performers. Now we can also do it as a permutation. Select 6 out of 6. In other words, let's do that first. Why not, right? So 6, this is the permutation. Select 6 out of 6 equals 720. That's why after we understand it, it's much easier to do it using calculator. So in other words, if you select 6 out of 6, it's the same as 6 factorial. If you select n out of n, it's the same as n factorial. Now let's look at our next example. In a race in which 6 automobiles are entered and there are no ties, in how many ways can the first 3 finishers come in? So this is a very common scenario. Actually, this is equivalent to how many different ways to select 3 winners out of 6 racers, right? Pretty much like that. And in a race, order definitely matter. ABC, among the same 3 automobiles, who is the first, who is second, order matters a lot, even though for the same 3 racers, right? So you know that. So we select 3 out of 6 and order matters. That's how simple it is after we understand this. So 6, select 3 equals 120. There are 120 different ways to identify the first 3 finishers, who is first, who is second. Anybody could be in the first 3. Just the order they appear is different. There are totally 120 different ways to line them up. Now, another one, a company's computer passwords must consist of 4 letters with no repetition of letters. That means among the 26-letter alphabet, no letter can be used twice in a given password. They're all different. How many different passwords are possible? Think about that. And you can use a fundamental counting principle because your password has to consist of 4 letters. You can choose those 4 letters one by one. Or you can use the permutation because you just choose 4 letters out of 26. Choose certain number of items out of another certain number of items. That by itself is a part of a permutation or combination, depending on if order among the 4 letters make difference or not. In this case, it makes difference because it's a password. So we choose 6 out of 26. Choose 4, out of 26. So let's do that, 26. Let's see how many passwords we can have. Different passwords. 358,800. That's not small number, just for 4 letters. If you add 1 more letter, that's way more than this. Way more than this. That's why when you go shopping online, and if you pay attention, sometimes the website are usually on the bottom about the security of your credit card. When you use your credit card, they would say our system is using something like 32-bit encryption. What that means, 32 bits encryption. That means each bit is either 0 or 1. So for each bit, there's 2 possible outcomes, but you have 32 bits. That's 2 to the 32. That's how many different numbers possible. Let's do that to see what we get. 2 to the power of 32. I don't know if you can read that number or not. Among all of these possible 0, 1, 1, 0, those lineups, there's only one that is correct. So in other words, if there's a thief, somebody try to crack your all of your credit card numbers, each number they have to guess this many times in order just for that one number to be correct. And they have to guess all of your credit card number correct in order to access your credit card number. That's how safe it is. I can give that person 10 years to do that, to be correct. That's why they already try to deceive you to let you tell them your password instead of hacking into your account. It's very hard. But for smaller websites, they don't have enough either technology or especially money to do that. It costs money to buy that technology to encrypt the transactions. Okay, anyway, this is our answer. Let's do another one. The board of directors of a corporation must select a president, a secretary, and a treasurer. In many possible ways can this be accomplished if there are 18 members on the board of directors. Simply put, we need to select 3 people out of 18 people to be president, secretary, and treasurer. Does order matter or not? We mentioned one of the similar examples before. Whenever the selected person, selected people, they play different roles, they assume different positions, order matters. We already mentioned that Biden being president and versus Harris being president, only even though they are same 2 people, but order makes huge difference because they assume different roles, right? So we select 3 out of 18 and order matters. So very simple. 4896. That's how many different ways to select these 3, to fill these 3 positions actually. Okay, the last one we have here for this video. How many arrangements? Each arrangement is called a permutation, okay, or combination in the next video. How many arrangements can be made using 4 of the letters of the word, this word combined, if no letter is to be used more than once? Remember, the basic requirement being a permutation is no item can be used twice, right, or more. So basically, we are going to choose 4 letters and arrange those 4 letters. How many different ways to arrange 4 letters out of this? How many? 1, 2, 7 letters. They're all different, right? In other words, each time you pick 4 letters, and they ask you how many different ways to have different 4 letters arrangement, as long as those arrangement are not repeating. Since order makes difference, so for example, COMB versus CMBO are considered to be 2 different results because order matters. Okay, order matters, we choose 4 out of 7. That's all it is. If you see the nature of this kind of problem. $840. So 840 different ways to arrange 4 letters out of this word. And see you guys in the next video.